Now, if A is an n by n matrix and X is a vector in Rn, so if you see the Rn, Rn basically means a vector space, all right? You actually learned the vector space before. R, for example, if I give you R3, R3 means a set of values in the form X, Y, Z, such that X, Y, and Z, they are all real numbers. So this is what you call R3. So you learned this before. For example, the vectors. So you can say that this is, let's say, vector A, which is equal to 1, 2, and 3. So 1, 2, and 3 means I plus 2j plus 3k. So this will be an element in R3. So what is R2? R2 means you have any vector in the form x, y, like that, where x and y are both real numbers. So actually the Rn you have learned before. So if I talk about R4, basically means you got 4 values there. So it's actually a column vector in the form x, y, z. So we have one more element at the fourth row. You call it t. So in this case, you have x, y, z, t, and they are all real numbers. That's why you call it R4. Okay. There is usually no general geometric relationship between the vector x and also the vector ax. Okay. However, there are often certain non-zero vectors x and ax are scalar multiples of one another. Such vectors arise naturally in the study of vibrations, electrical systems, genetics, blah, blah, blah. Okay. In this section, we shall show how to find these vectors and we shall touch on some of the applications. All right. So let's look at the definition. Yeah. All right. Now, if A is an n by n matrix, then a non-zero vector x in Rn is called
Excuse me,
an
sir. Sorry.
eigen. Yes.
Could you please let Danish in?
Danish. Okay. Full attendance. So you have ax equals to lambda x. Now, this is the most important thing here. Huh? The ax equals to lambda x. All of you can see. Ax equals to lambda x. So you see, you have this value lambda. Okay. So lambda is what you call the eigenvalue of the matrix A. And x is what you call the eigenvector of the matrix A. So the lambda and the x, they exist together, all right? So you have to define the eigenvalue and eigenvector together, all right? So in this case, we have ax equals to a scalar multiple of x. So basically, it means like this. I have a times the vector x, all right? This somehow give you a scalar multiple of the x. Then you say that lambda is the eigen value of the matrix A. And x is known as the eigen vector of the matrix A. And remember, eigenvalue, eigenvector, they must be defined together. They coexist together, all right? So now we continue. Suppose that now I want to find what is this lambda, because I need to have the eigenvalue, all right? So I want to find what are the possible lambda values such that A times the vector x is equal to lambda times the x, scalar multiple of x. So in order to find the eigenvalue, what we do is we have A x minus lambda x is equal to 0 vector. Now, what happened is I'm going to introduce a matrix I. So you see that AX is actually AX minus lambda. So I introduce the I here. So I add in the I. Okay? So that I can actually factorize the X. So this is a matrix factorization. So you have to make sure that the x is at the back, okay? Then you have A minus lambda I. You see, A is a matrix. So you cannot say A minus lambda. This is a matrix. This is a real number. So you will never have a matrix minus a real number. So in this case, what happened is you have to introduce the I, all right? So that you have the subtraction of matrices. So you have A minus lambda I times X is equal to 0 vector. Now, let's say I call this B, all right? So I let B equal A minus lambda I. You see, the matrix A minus lambda times the identity matrix. I is the identity matrix, yeah? So I now have to solve B times X is equal to 0 vector, all right? So Bx equals to 0 vector. There are two situations, okay? So the first situation is when B is non-singular. Do you remember what is the meaning of a matrix that is non-singular? What does that mean? If B is non-singular, that means, can anyone recall? Non
Determinant of B is not equal to 0.
Okay, determinant of B is not equal to 0. Okay, what else can you deduce? When I said B is non-singular, that means the determinant of B is not equal to 0. Therefore, what else you can deduce? There is a
Inverse.
B
inverse,
inverse
all right?
exit.
Yes, B inverse exists. Okay, so this is how I solve the problem. If B inverse exists, that means in order to solve the equation B x equals to 0 vector, I can now put B inverse in front, right? So I have B inverse times the 0 vector. Okay, when B inverse and B together, so these two will cancel out and give you identity matrix. So you have identity matrix times the X is equal to, now what is B inverse times the 0 matrix? 0 matrix means all the elements in the matrix, they are all 0 lah. So B inverse times 0 matrix, what do you get? We have? What do we have?
0.
0 vector. Okay? Therefore, you get the conclusion that X is equal to 0 vector. Okay? So you know that X can always be equal to 0 vector in this case. But the question now is, I want to find a non-zero vector. Is it possible or not? So that gives us the second possibility. To find a non-zero vector such that Bx equals to 0 has solution. Therefore, just now we assume that B is non-singular. Therefore, in this case, B must be singular, right? So if B is singular, what does it mean? If the matrix B is singular, it means
Determinant of B is equal to 0.
okay, determinant of B is equal to 0. So just now we said that B is non-singular. Therefore, determinant of B is not equal to 0. Then you obtain the 0 solution. So in order to find a non-zero solution, the determinant of B must be equal to 0. Correct? And therefore, the story continues here. All right? This is the 0 solution. Okay? So when I say determinant of B is equal to 0, I know that B is actually A minus lambda I. Therefore, I must now set determinant of A minus lambda I equals to 0. So we use the determinant of A minus lambda I to find the eigenvalue lambda. So this is used to find lambda. So the lambda is what you call the eigenvalue, correct? So now we proceed. Suppose that I ask you to find the determinant of A minus lambda I, all right? What are you going to get when you have the determinant of A minus lambda I? Okay, so now I explained this part already. So that's the reason why you obtain this. Let me check if I can use right on PDF. Okay, so just now I explained this part already, all right? So for lambda to be an eigenvalue, this part, there must be a non-zero solution to this equation. That's why just now I keep on talking about non-zero vector. So you have to set determinant of A minus lambda I equals to 0. Okay, so we proceed with the definition. Now this is what you call the characteristic equation of A. The scalars satisfying the equation are the eigenvalues of A. So the scalars that they're talking about here is the lambda. So in other words, you have to find lambda. So when expanded, the determinant of A minus lambda I is a polynomial in lambda called characteristic polynomial of A. So you are going to get a polynomial in lambda. And if A is a 2 by 2 matrix, the polynomial that you are going to get is a quadratic polynomial. If A is a 3 by 3 matrix, the polynomial you are going to get is a cubic polynomial. If A is a 4 by 4 matrix, then the polynomial that you are going to obtain is a quadratic polynomial. Okay, so it depends on how many rows and also columns there. So in general, if I have n by n matrix, the polynomial that I'm going to get is a polynomial of degree n. Okay, so now the next question is, how do I find the eigenvalues and also the eigenvector using the characteristic equation, right? So you must first find the characteristic equation. Okay, move on. Let's look at second page, right? So we are going to skip the 8 theorems first. Yeah? I will come back to the 8 theorems later. So today our main focus is to find the eigenvalues and also eigenvectors of a square matrix. So the first case we are going to look at is this one. Okay, case 1. Okay, case 1, 2 by 2 matrix. Okay, now the characteristic equation determinant of A minus lambda I equals to 0 is a quadratic equation. Only real and distinct eigenvalues are considered. So in our syllabus, we only consider real and also distinct values of lambda. So an eigenvector is a solution of Ax equals to lambda x. Hence, to find an eigenvector corresponding to lambda equals to lambda 1, you have to find a column vector xy satisfying the equation Ax equals to lambda 1x. So this is actually to solve the simultaneous equation. Okay, so I will show you later how do we solve the equations. But first of all, you need to know how to find the quadratic equation, because the first thing you have to find is the characteristic equation, determinant of A minus lambda I equals to 0. So suppose that I call my matrix A equals to, okay, A equals to, let's say A, B, C, D, right? So this is a 2 by 2 matrix. All right, so I'm going to consider this matrix. So now we move on to find characteristic equation of A. So how do you find? So case 1, I would consider A equals to A, B, C, D, which is a 2 by 2 matrix. Okay, so the first thing you have to consider is I need to have the matrix A minus lambda I. So when you have A minus lambda I, it means A, B, C, D minus lambda times. Now I means 1, 0, 0, 1, which is the identity. So therefore, you will see that this is A minus lambda, this is C. Then this is D minus lambda, this is B. Okay, So you see, only the diagonals are affected because only the diagonals are non-zero. The rest are all zero. And don't forget, the 1 has to multiply by the lambda. Therefore, I have a minus lambda, d minus lambda here. Okay? So after getting this one, you are going to find the determinant. So the determinant means the AD minus the BC, right? So determinant of A minus lambda I is equal to A minus lambda, D minus lambda minus B times C, right? So you see or not, this is actually a quadratic equation. So it's a quadratic polynomial. So the characteristic equation of A, when A is a 2 by 2 matrix, is a quadratic polynomial, right? Then after that, you move on with the solution. So you have to set the determinant of A minus lambda I equals to 0. So after that, you will have to solve the equation A minus lambda, and then D minus lambda, and then minus C equals to 0. So in this case, you solve, you will get lambda equals to lambda 1 and also lambda 2. So if you have a 2 by 2 matrix, you are going to have 2 eigenvalues. If you have 3 by 3 matrix, you are going to have 3 eigenvalues. So if you have 3 eigenvalues, that means you are going to have 3 eigenvectors. If you have 2 eigenvalues, that means you are going to have 2 eigenvectors. Because I told you, eigenvalue and eigenvectors, they exist together in a pair, as a pair. All right. So the next question is, after you solve the quadratic polynomial, how do you find the eigenvector? So to find eigenvector, so let's say now I want to find the eigenvector corresponding to the first eigenvalue, to lambda equals to lambda 1. So what you do is you have to solve the equation, which gives you A minus lambda I equals to 0 vector, correct? Because we use this one, right? A minus lambda I. So you are going to get, sub in the lambda 1 value. So you have A minus lambda 1 value. This is C. This is D minus the lambda 1 value that you found. This is D. Then you multiply by the X, Y. And this will give you 0 vector. Hey, sorry. I think my notation here, something not right. So this should be A minus lambda I times the X, and this is equal to 0 vector. Okay, so the X here means the eigenvalue. So this is the eigenvalue. So you can find the eigenvalue which has 2 components. So the X component and the Y component. So this is what you call the eigenvector. So you have to solve this equation. So when you solve the equation, you are going to get 2 equations. So you solve for the 2 equations. Okay. So you are going to get the 2 equations. The first one would be A minus lambda 1 times X plus dy equals to 0. Because 0 vector means both of them are 0, right? So the second equation, this is equation 1. Then the second equation is Cx plus d minus lambda 1 times the y equals to 0. So this is the second equation. So you solve 1 and 2 simultaneously. Okay, and this is the overall process for a 2 by 2 matrix of A in the form of A, B, C, D. So first of all, you must find what is A minus lambda I. Okay, after that, you find the determinant of A minus lambda I. Then you set the determinant of A minus lambda I equals to 0. Then you solve the quadratic polynomial equation. So you will get 2 values. So you have to find the eigenvector corresponding to lambda 1 and lambda 2. So it's a very time-consuming process because you have to find eigenvector corresponding to lambda 1 first, followed by the eigenvector corresponding to lambda 2. You have to find separately, no choice. Okay? So in this case, I will show you one example, right? So we go to the next part. We go to the first example first. Okay, let's look at this 2 by 2 matrix. Find the eigenvalues of the matrix. So I give you the matrix here. 4, 3, -2, -1. Now let's say I call this matrix A to make our life easier, because I'm going to use the notation A minus lambda I, determinant of A minus lambda I, and so on. So I will call this matrix A. And then the second part is find the corresponding eigenvectors. Now you know that this is a 2 by 2 matrix. So you are going to have 2 eigenvectors. You are going to have 2 eigenvalues. So 2 eigenvalues, 2 eigenvectors. So now we have to find the first one. All right. How do we find the eigenvalues? You must always think of getting the matrix A minus lambda I first. Then after that, followed by the determinant of A minus lambda I, and you set this equal to 0. Okay. So let's start with this one. So this is 4, 3, -2, -1. So example number 1. Okay. Example number 1. Right. So I will write down A minus lambda I straight away. So I have 4 minus lambda. Then this is -1 minus lambda. I think this is -2. This is 3. So this is the A minus lambda I matrix. You don't have to copy the matrix A and then minus the lambda I as what I told you just now. Like what I told you just now, you know that you are going to subtract the lambda at the diagonal. So therefore, you only look at the diagonal. The rest will just follow lah. So this is what I mean by the diagonal. So the diagonal subtract lambda. So I have determinant of A minus lambda I. So you have determinant of A minus lambda I, and I set this equal to 0. This is used to find the characteristic equation, and then you solve the characteristic equation. That would give us the lambda value. So the determinant of A minus lambda I, this is a 2 by 2 matrix, so you can use 4 minus lambda multiplied by -1 minus lambda, and then minus -2 times 3, and this is equal to 0. Right, you need to simplify this part. All right, so can you please simplify for me and give me the final form? I think you get lambda squared. Yeah, never mind, I do lah. Later we make mistake and then cannot get the answer, worse. So I have 4 times -1 is -4. 4 times negative lambda is -4 lambda. Then minus lambda times -1, you get positive lambda. Then minus lambda times negative lambda, you get positive lambda squared. So this one is double negative, gives you positive. 2 times 3, you get 6. So plus 6. So the characteristic equation should be in the form of lambda squared. -4 plus 1 is -3 lambda. Then -4 plus 6 gives you +2 equals to 0. Okay. So you can factorize this. This is quite easy to factorize. Lambda 1, lambda 2. So -1, -2, I think. -1, -2, -3, +2. Yeah, correct. So therefore, you get the 2 lambda values. Therefore, the eigenvalues are 1 or 2. Now you only found the eigenvalues. According to the question, they ask you to find the eigenvalues followed by their corresponding eigenvectors. Okay, so now I am going to define eigenvectors. All right, so let's say I define this way lah. Let E I denote the eigenvector corresponding to eigenvalue lambda I, where I equals to 1, 2. Because you got 2 eigenvalues here. So I equals to 1, I equals to 2. All right. So now we are ready to find the first set of eigenvectors. All right. So continue. So let E1 be x1, y1. Okay, I think no need lah. Just find x, y. That is good enough. Right. So this is the eigenvector xy correspond to eigenvalue lambda 1 because my I is equal to 1 now. This is EI. All right. So I am going to use, yeah, I think I better put down case 1, case 2, easier for you. Okay. Case 1. Now we talk about lambda 1 equals to 1. So we are going to talk about the first one. Okay. So you have A minus lambda 1 I times the first eigenvector E1 is equal to 0 vector. We are using the definition here. All right. So we are using the definition here. This one. All right. A minus lambda I times x is equal to 0. So the x is the eigenvector. So in our example 1 here, our eigenvector, we call it E1, right? So now we put it this way. So the A minus lambda I means you take the value, you take the matrix just now, you have A minus lambda I. Lambda is equal to 1. So you put in 1 inside, you get 4 minus 1, you get 3. So you get 3 and 3. Then you have minus 2 and minus 1, so you get minus 2, minus 2 times the eigenvector 1 in the form of x, y. This is equal to 0, 0. 0 vector means 0, 0. Okay. So now, how much time left? Okay. Should be able to complete this one. So I have, therefore, you expand, you get only one equation. All right. You get only one equation because you see the first line, second line, they are the same thing. So you get 3x minus 2y equals to 0. You only get one equation, so you don't have to panic. That is actually better. That means you will have a lot. You can give me different answers. So in this case, what happened is I can express y. I express y in terms of x. Therefore, I get y is equal to 3 over 2x. Right? Am I right? Y 3 over 2x. Yes. So you see, therefore, our eigenvector 1, which is originally in the form of xy, now can be written as x and 3 over 2x. Am I right? Because you sub the y equals to 3 over 2x into the second row, y here. Okay? Therefore, you get 3 over 2x. And you see my eigenvector 1, I think I shouldn't put equal first. So the eigenvector 1, I think I put it this way. So the solution is in the form of xy, which is equal to 3, which is equal to x followed by 3 over 2x. So you can factorize the x and over 2. So in the solution here, I know that this is 2. I know that this is 3. So in this case, right, you take the number, 2, 3 as our eigenvector. So this one will be our eigenvector 2, 3. That is the first answer. Okay. So you take this 2, 3 without considering the x over 2. This is not important. Okay. However, please remember that eigenvectors are not unique. That means if let's say some other students gave me the eigenvector in the form 4, 6 is acceptable. Even if you give me -2, -3 is also acceptable. If you want to give me 200 and 300, still correct. So that's why you have to remember, eigenvectors are not unique. They can be different in sign, can be different in terms of magnitude, but you must make sure all of them are, okay, in the vector, then we say that they are parallel. They look like parallel, right? 2, 3, 4, 6, -2, -3, 200, 300, they are all parallel, correct? You make sure that they are parallel, okay? Or you make sure that they are scalar multiple of each other. So even if you want to give me the answer, for example, 1 and 1.5 is still okay. So your E1 can be 2, 3, can be 1, 1.5, can be 4, 6, can be -2, -3, can be 200, 300, they are all okay. But of course, we will try to pick the number which is the easiest for us. In this case, E1 equals to 2, 3. Because later on, you may need to use the eigenvectors to generate inverse matrix. Inverse matrix. So you imagine if you go and use 4 and 6, then the inverse matrix will look a bit weird or different. Okay, so that is actually the first case. So the first eigenvector is found. Now we go to the second case. So for second case, case 2, you have lambda 2 equals to 2. So this is case 2. So you are going to do the same thing. So what do I mean by the same thing? A minus lambda I times the vector, the eigenvector, equals to 0 vector. So we are going to do it this way. So I have A minus lambda I. So A minus lambda I. So you go back to your A minus lambda I. A minus lambda I is here. Okay. So now you put in the lambda equals to 2. So you get the first one is 4 minus 2. So you get 2. So first column is 2, 3. Second column, you have -2, and then you have -1, -2. So -2, -3. So -2, -3. So multiply by the eigenvector in the form x, y. This will give you 0 vector. Okay, and therefore you can now see that this is also one equation only, even though you can see that they look like 2. Okay, I write down both for you. Okay, I write down both for you. So I have the first line is 2x minus 2y equals to 0. The second line is 3x minus 3y equals to 0. Even though you get two different equations, but after you simplify, right, you will only have one result. The result is x equals to y. Am I right? So you know that our matrix xy can be expressed as x and x because your y is equal to x. So how do you generate the eigenvector? So you take out the x, you have 1, 1. So you take this as the eigenvector 2. So therefore, eigenvector 2 is equal to 1, 1, corresponding to this value. Lambda 2 equals to 2. Okay. So far, any problem? Okay. I am going to end the first session, okay, and then 5 minutes break. Then we go to the second session. All right. Thank you. I will send you this document after the second